Okay. Well, just spontaneously, when I hit that, the camera zoomed back. So you got to look at my whole face while I'm talking. And I do apologize for that. I know it could be traumatic. Okay, anyhow. So what we're doing here in this last phase of the course, there are two things that cause people not to do as well as they should in pre-calculus. One is the inability to do algebra and just basic mathematics, okay? And the exercises we're doing right now will kind of reinforce the basic rules, because a lot of people are still not seeing the basic rules every time they come up. And they come up here in a very simple way, okay, just with numbers, okay? And I'm talking about basic rules for dealing with fractions. How do you divide by a fraction? Okay, basic rules for exponents. What's a negative exponent mean? What are the rules for exponents? Okay, we got to know those things. So we've done that with rational functions and everything else. And y'all have done pretty well with it. Some of you done very well with it. So I just feel a little shaky on it, which is to be expected. Okay, so we're going to go back and reinforce these rules with just plain old numbers, but we're going to do it in the context of functions, okay? Pre-calculus functions, the functions that kind of rule the world at the level of pre-calculus and calculus, okay? These functions are basic to everything you do, and we're trying to give you an overview of pre-calculus, okay? So that's what we're developing here, and you'll see how that works out. So this is very important stuff. Now, for this quick quiz, I'm giving you one of the basic functions that you maybe encountered if you got the homework done. Okay, some people say they have a little trouble with the homework, and we'll try to deal with that. Okay, so you have this. And when we do a basic function in my class, we're always going to just use these numbers. Now, your textbook and your open math assignments will sometimes use a broader range of numbers. We're going to confine ourselves to this range of numbers from -2 to 2. And we're going to include these 7 numbers, like -2, -1, 1 and 2, and then 0. -2, -1, 0, 1 and 2. But we're also throwing -1/2 and 1/2 in. And when we do this graph, you're going to see the importance of the -1/2 and the 1/2. With some functions, as we said, and as we talked about last time, the exponential function, for example, you can't evaluate it at -1/2 and 1/2 except by punching buttons in your calculator. And we're not punching buttons on the calculator. We're using the basic arithmetic that a 5th grader can do, if they've got the rules. Most 5th graders don't have the rules like you do. And, you know, as I've said, they put a calculator in your hand before you can walk, so you don't have to do arithmetic. Okay? Terrible, terrible, terrible. You will never understand these functions unless you understand the arithmetic. It's all based on arithmetic, and arithmetic is not something that's done on a calculator. Now, sometimes you got to use a calculator. If you want to do the basic exponential function for 1/2, what's 2 to the 1/2 power? Well, it's the square root of 2, but you know, what are some other things to the 1/2 power? You can't do 2 to the 1/2 power by hand. First place, it's the answer is infinitely long, and you got several calculations to get every digit. So it'll take you a while to get the exact value, and you still won't really understand it because you got to understand calculus before you understand how that's calculated. Okay? So we don't use it if we can't calculate it. Now, for this function, you can calculate the 1/2 power and the -1/2 power. It's very easy. Doesn't mean that you're up on the rules and can do it. By the time we're done, you should know how to do that. If we have the function, the 1/x function, which we looked at last time, you can't do 1/0. If you divide 1 by a small number, you get a big result. Well, 0 is infinitely small, so you get an infinitely big result. Okay, that's one way to understand it. So anyhow, I want you to understand the context and why we're switching gears to these functions, and in 3 weeks, we should get a pretty good overall understanding of a pretty good context. We're trying to develop a context that you can use in pre-calculus, so everything you do, you have a pretty good idea how it fits in, okay? So we're kind of done with this tricky algebra. And I know that, that you're going to be really sad about that. We're kind of done with the difficult algebra. You've gotten a good bit of it. Your brain has been over it. Some of you are going to need the support course when you take the pre-calculus. Some of you I don't think will. Okay. And I'll talk about that with you individually anytime. Okay. I don't know yet. You haven't done the final exam, but there are some people I would certainly bet on being able to do the course without the support course. Some people I'm pretty sure are going to need that support course. Okay. So there's where we are. And this is what we're doing for the last few weeks. And so I apologize for taking quiz time at this point, but a lot of people missed last time. I want everybody to understand where we are and what we're doing and why we're doing it. Make sense? Okay. This is my former student. She promises not to be as disruptive as you all are. Okay. So go to it. Let's see what you do with this problem. And I'll be circulating, looking over your shoulder. I'm glad as many of you showed up as did, because if only 2 of you had showed up, and that's never happened, the average attendance here is at least 5. Okay. And usually 6. If only 2 of you showed up, I'd be over your shoulder all the time. You wouldn't be able to think. Okay. So go to it. And I'll give you a few minutes to get started and see how you do. Now again, take the table. Construct the graph. I'll also give you the hint that every one of these numbers will fit into here. Okay. So there's no number that needs to be excluded for this function. Now I'm going to see if I can get the camera to zoom properly and stop the recording. So as usual, it'll focus on a pretty picture. Okay. So everybody did a great job over here. Okay. Now, the way I ask you to write this out is you got -2 cubed, which is -2 times -2 times -2, -2, which is -8. Okay. So I'm not going to write that out for every step because I did that in the original video on Monday for different functions. But you know, I want to see this because, as I said, at least one person, I get worried if I don't see this. Okay. Because I'm worried that you just remember what the numbers are and have lost track of why they are. Okay. So anyhow, -1 cubed is -1, -1/2 cubed is -1/8. 0 cubed is 0, and then you get 1/8 and 1 and 8. And everybody got that. Okay, that's very good. Then you set up your graph. Here's your y-axis, and here's your x-axis. I start with my extreme values. Now I'm going to use a little terminology on you. I used it before. These numbers are your domain. Okay. And that's one of the concepts we want to introduce today. So domain is the set. Now, we haven't talked about sets or set theory or any of that. Hopefully you've seen it at some point if you've had the prerequisite courses, but maybe not. And maybe if you did, it wasn't emphasized as much as I would prefer. Okay, I'm starting to get in the way of my graph here because, as usual, I don't plan very well. But there we have it. Okay, that's your domain. It's your x values. Okay, your range is your y values. So your range is -8, -1, -1/8, 0, 1/8, 1/8. When you write these down, you want to do yourself a favor and keep them in order. Now, for this function, they just naturally occur in order. For some functions, they start high, go low, and go back high, like the x-squared function, okay? We'll see how you do the domain on that. There's a little anomaly, not an anomaly, but something you want to be sure you understand. Okay, so anyhow, there it is. So that's domain and range, very simple. So I'm going to put -8 here. And I put it here for a very good reason. I'm going to need the point -2, -8, and I've got a hole here where I can put it between what I've just written. Shouldn't have written it like this, but I don't always anticipate what I'm going to see out there, so I don't always anticipate what I'm going to write. And even if I do it wrong. Okay. So you got -2, -8. Well, we can go ahead and put that point down here. Okay, well then you subdivide these intervals. Subdivide the interval from 0 to 2 to get 1. From 0 to -2, you get -1. And we get -1/2 here and 1/2 here. I wrote the -1/2 up here because I know I'm going to have to write a number just below the axis here. I don't want it to interfere with that. Of course, I already wrote -1 down here, and that's going to get in the way too, but we're going to just live with it. Okay. So we got -8 here. I wrote 8. Okay, we got to go equal height up here. So 8 is going to end up around here. The arrow really should go up a little higher. And then we get subdivide the interval here. We get 4. Subdivide this interval in half. We get 2. And then we get 1. And we've got to get 1/8. Okay. How are we going to get 1/8? Well, here's 1. Subdivide that in half. That's 1/2. Divide that in half, we get 1/4, and divide that in half, we get 1/8. So 1/8 is really close to the x-axis, so close that it's almost in the line I drew. Okay. And one reason we do this exercise is this interval is big enough that we can actually locate 1/8, right? So let's just digress to this because everybody understands what I'm doing so far. So I'm mainly talking to people who aren't here because there's 1 or 2 people who are. Okay, not labeled really clearly because it's hard to squeeze things in down here. But there's 1/4 and there's 1/8. So now our points are 0, 0, 1/2, 1/8, and 1, 1. Now, if I want to draw the curve for this thing, it'll be pretty flat in here. Okay, which means that when you draw this, you're going to want to make it really flat between -1/2 and 1/2, almost on the axis, if you want it to be accurate. Now, it's not totally important that it be really accurate, okay, when you sketch it. So the graph's supposed to be sketched here, even though it wasn't flat enough, it's a serviceable graph, unless you want to look inside this interval. Okay, well, we go ahead and plot. Okay, so here we have this point and this point and this point here, which is really close to the x-axis. So close that, as usual, I'm going to change colors on you so we can really see where these points are. Okay, well, I haven't done the subdivision down here, but we see -1 is going to go about here. So you're going to have a point about here and a point down here. And now, if you want to draw the curve, you've got a set of points you can go through. We can leave this one too. So the curve gets a lot flatter than most of you drew. Okay, and if you look here, you see why that is. You notice also if you did the x-squared function, if this is x-squared, you'd have 1/4 here, right? So the x-squared function would go through this point. It wouldn't be nearly as flat course, in the x squared function, you have a parabola, and it'll naturally flatten out that way, unlike this function, okay? Now, in the future, you're going to see, and maybe the near future, depending how far we get today, you're going to see that if this is an even power, it's going to be like x squared, except at the negative 1/2 and 1/2, you're going to get 1/16, which flattens this thing out even more than this, okay? Flattens it out twice as much, where it looks like it's almost square, okay? And it would be positive, the y values would be positive on both sides because you're taking an even power of a negative number over here, okay? So for any even power, the thing flattens out, and the higher the power, the more it flattens out, to where if you have a really high power, the thing almost comes down vertically, goes over here and up, almost like a rectangle, okay? For an odd power, well, what you have over here is kind of a reflection of what you have here. If you reflect every point through the origin, you get a point down here, okay? Now, that's something that probably go over your head right now. Although you understand it right now, you probably won't remember it later, and I'm not going to test you on it. But it's worth thinking about because when you get into pre-calculus, you're going to have to use tests for even and odd functions and understand what it means to reflect a point through the origin. So all I'm saying is, if you draw a line from this point to this point, it goes through the origin. And you have equal distance on this side and this side. So this point reflects through the origin. This one reflects through the origin. For the x squared function, everything reflects across the y-axis. And it's not too hard to see that. And it's something you, even if you forget it between now and pre-calculus, it's something you want your brain to start working on now. Okay, again, our big purpose these last 3 weeks is give you the ideas that you're going to have to use in pre-calculus, so that unlike most students, you will have at least thought about these things a little bit. And then when you get them in pre-calculus, you don't have to think as hard and you can concentrate on other things and you're going to be more successful, okay? So that's really where we are for these last 3 weeks. What we've done with the tricky algebra is done. You've picked up more or less, and it doesn't mean you're not going to have to bone up for it for an exam. Okay. Anyhow, there it is. There's this graph. Now what can we do with this graph? Okay. I want you to estimate with whatever graph you have, what's the value of y equals x cubed. X equals 1.6. I'm going to give you a minute, just a minute, to see if you can show me how you would use this graph to answer this question. Of course, you could always put that into your calculator, and that's what you would practically do if you wanted an accurate result, okay? But we want to see how that comes out on the graph. Okay, so here's what I would do. A couple of you did it, and a couple of you were very close. And at least one of you was right on track, and I think you probably ended up doing it. Okay, where's 1.6? X equals 1.6 is going to be on the x-axis, right? It's going to be between x equals 1 and x equals 2. Well, we could subdivide this to get x equals 1.5, right? And then we divide this interval into 5 parts, more or less accurately. And we're going to say, okay, here's where x equals 1.6. My arrow didn't quite point right. I can't get the chalk to cooperate as well as I'd like. But if I do this, okay, well, that's going to come out really good. And I didn't fudge it. Okay. So we come over here. It looks like we just pretty much hit 4. Okay. And the accurate result is just a little over 4. It's like 4.1 if you round it off. So I just lucked out. But the other thing is, the shape of my graph is a little better than the shape of most of your graphs because I knew in advance I had to flatten it out. Of course, you know, we worked that out, why we flatten it out. And flattening it out here gave me something that I could get a good estimate off of, although it was pure luck that I got that close. Okay, I'm not that good. But I probably would have been within a quarter of a unit with a hand-drawn graph. Okay, so this is how you can estimate the value of the function. Okay, let me ask another question. What value of x is x cubed equal to 6? Anyhow, just in case I didn't have the camera on, x equals 1.6 occurs about here. I just subdivided this interval in half, then divided this part of the interval into 5 parts. So we have this, okay? Then to see what the y value is, I just go up to the graph and project over here, and I estimated 4. That was a dumb luck, accurate estimate. Okay, as I said, since the camera wasn't on, I'll say it briefly now. By knowing how flat to make this graph down here, my graph had a little better shape than most of yours. Okay, no offense. Next time yours will be even better. Okay, but this allowed me to estimate the value of y for x equals 1.6, and y is the value of x cubed. Now, my current question is, for what value of x is x cubed equal to 6? Okay, and let's note that this function is y equals x cubed. Now, there's function notation involved here, and we'll get into that depending on what we see here. Okay, I want to introduce that idea. But let's see how you do with that. Okay, we're looking for the value of x that makes x cubed equal to 6. Well, x cubed is y. Don't ask why. Okay, x cubed is y. So we want to know when y equals 6. So we want to look up here at y equals 6. Well, here's 4, here's 8, here's 6. Now, I don't honestly know what the cube root of 6 is, because that's actually what we're finding. And I'll just comment on that in a minute. But if I do this, according to my markings here, that's pretty close to 1.7. Okay. Now, there are plenty of calculus connections to this I'm tempted to go into, but I'm obviously not going to do that. I don't want to destroy your confidence. Okay. And I don't think I would. You have a lot of good reasons for confidence. But, okay, so here's the line for y equals 6. Okay. And incidentally, I'll throw this in. This line is the line where x equals 1.6. Everywhere on this dotted line, if it's vertical, it goes through this point. That's where x equals 1.6. This is where y equals 6. And when y equals 6, it comes down to the line where x equals 1.7. Now I use a little wavy bar with the equal sign to indicate it's approximately 1.7. This line is x equals 1.6. And they're not perfectly parallel, but we just live with that. The principle is that this calculation goes along the line where y equals 6 of this estimate, and then goes down to find out what x is. Okay. And this shows me that x is approximately 1.7. So I'll say x is approximately 1.7 if y equals 6. Graph is getting a little crowded here. But that's the idea. Okay. Now, if you carry these two ideas with you into pre-calculus, you're going to understand a lot about what the graphs are telling you. Okay. Okay. So we've seen the concepts of domain and range. Here's the domain that corresponds to this table, right? And here's the range that corresponds to the table. When I draw the curve, I've extended the domain. Now the domain includes all x values because I have y value for every x value, and I can use the graph to estimate values of x for a given y and values of y for a given x. Okay, so now my domain I hope I have this in the recording yet. I lose track of that. Okay, the domain, and after all this time, I really shouldn't. Okay, the domain of the curve, and we're talking about the curve over here, is the interval from -2 to 2. And I should say the x interval, just to be sure that we understand this is an x interval, okay? And this notation, I used brackets, okay? Now, when I wrote sets, I used braces. I use braces if I'm listing my numbers, but I can use brackets because I can't list all the numbers between -2 and -2, and I should have said -2 and +2. Okay? It's all the numbers between -2 and 2. Okay? And that's an interval. You're going to see that in some of your homework. Now, I use a terminology in my class, but you might not be in my class, so you don't have to know this terminology. I call this the extended basic function. Basic function is defined only these values, and there's its domain and there's its range. The extended basic function is this, okay? It's what we get when we extend this. We don't go beyond -2, we don't go beyond 2. It goes from here to here. Then there's the complete basic function, which is this thing for all values. So if x equals 6, as Alex discovered, you get 216, right? And that's kind of hard to see on this graph. It's, half a mile up. Well, not that high, but higher than you want to fall from. Okay, higher than most people can jump. Okay. And if you could jump that high, you'd probably hurt yourself coming down. Okay, well, anyhow. Make sense? In the range, is your y values. It's the y interval from -8 to 8. Okay. And then the complete function. Okay. It's complete cubing function. The domain goes from -infinity to infinity. I don't use square brackets in this because -infinity is not a number. Okay, so it's not included in the domain, but everything up to that is included to the left and right. You'll see more about that notation, and it's an easy notation to understand when you do the homework. So there's your domain, and the range is also from negative infinity to infinity. And I think that's still on the, yeah. So that's the idea of domain and range. One other comment, just to bring this into some of the recent stuff we did. We're going to say then that if y equals 6 when x equals 1.7, okay, that means 1.7 cubed is 6, right? Then 1.7 is a cube root of 6. Okay, now you can just relate that. I'm not even going to write it out, partly because I don't have a good place to write it, but I'm mentioning it. And that's, of course, x to the 1/3 power, right? So we've got it. Okay, just for a quick summary then. If x is 1.6, we can find x equals 1.6 here, go up to the graph and over, and we find 1.6 cubed, approximately. Okay. If we want an accurate result, of course, we go to our calculator. But when we go to our calculator, if we kind of have this graph in our head, we can tell if the calculator is giving us anything that makes sense at all. Because a lot of times it won't. And it's important. I won't say it's necessarily crucially important, but it's extremely useful. Like if you want to make an A rather than a C, that you not make errors in the calculator, that you could easily check if you were thinking. Okay. So if you can think this graph and kind of visualize it and just realize that this tells us that if x is 1.6, x cubed is 487, say no. Yeah, 1.6 is on this graph and stuff like that. It's useful to be able to do that. That's a stretch. So I'm just going to mention it, but kind of note that. Okay. Now, okay, that's pretty much all I want to say about this because there's quite a bit, except, just to re-emphasize, if you want to find the value of x so that x cubed is 6, well, x cubed is a y value in this graph. So you go to 6 and you go over and down and you find that x is about 1.7. Somebody got a calculator handy? Can you cube 1.7 for me? Just to see. Okay. I want to talk
4.913.
again.
4.913.
4.913. I lucked out on that one too. Okay. No, I didn't. No, because that's close to 5, and I got that as 6, right?
Yeah.
So I didn't luck out. And that shows you my real skill. Okay. Shows you what I'm really worth, which is something, but not all that much. Okay. Now, let's go back to the graph that we did in class last time. And if you missed class and haven't seen the video, you really want to do that, okay? Because I'm just going to have to refer to something because I don't have time to develop the graph, but it's on the video and people didn't have any trouble. But people actually pleasantly surprised me by doing it almost as quickly as I asked it, okay? The graph of y equals 1 over x. Okay, well, I've got 2, I've got -2. I'm going to have 2 up here. I'm going to have -2 down here. Then I'm going to have 1. I'm not even going to label 1 and 1/2 because everybody knows what those are. You can see it on the graph. Assuming it's done right, who knows? Okay. So we got this point and 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 this point. Of course, I didn't anticipate where I should have labeled the -2. And if we draw the curve, we do this. But we don't attempt to connect this point to this point because 1 over 0 is not defined. If I connect this point to this point, I've got to go through the y-axis to do it. And that would tell me that 1 over 0 is whatever the value of y is when we choose to go through the y-axis, okay? And it doesn't have a value because you can't divide by 0. And that's because if you divide by a number really close to 0, you get a really big result. If you actually hit zero, the result becomes infinite. And it's not even a number, and it can't be displayed on a graph. Now that gives rise to asymptotes, and I just mentioned this. We're not, I'm not probably not going to test you over the idea of asymptotes, but it's worth storing away that if you keep going to smaller and smaller numbers, this thing just keeps going up, and it keeps going up forever. So you get a curve that gets closer and closer to the y-axis that never touches it. So it approaches being infinitely steep, and it never stops. You can get as close as you want to zero, and you get as high as you want. So we say that as x approaches zero, at least from the right-hand side, y approaches infinity. Okay. And if you approach zero from the left-hand side, well, y approaches negative infinity. It's an important idea. Again, I'm just trying to loosen up your brain with that idea right now, but it's worth loosening up because it's another thing that people in pre-calculus have no concept of. And I can't imagine how that is if they've had the prerequisite courses. I don't know what's going on in prerequisite courses these days. Okay, but that's not. Okay, they might memorize that there's an asymptote, but they don't understand why, and they don't seem to have the background that allows them to understand why. So I'm trying to give you a little bit of background that's actually going to give you some advantage when you get to these things. Also, if you keep going this way, 1 over x, you keep dividing 1 by a bigger and bigger number, you get a smaller and smaller fraction. Okay, the bigger x is, the smaller this fraction is. 1 over 100 is a lot smaller than 1 over a million. It's a lot bigger. 1 over a million is a lot smaller than 1 over 100. Okay, don't quote me on that. Okay, now I want to talk about the domain and range of this function. Okay, the domain of your table is just the numbers -2, -1, -1/2, 1/2, 1, 2. It doesn't include 0 because 1 over 0 is not defined. Okay? The range of your table is -2, -1, -1/2, 1/2, 1, 2. Because of course, if you do your table, and I'll write it out. I didn't put 1/2 in here, so it's kind of sloppy. Okay. When x is -2, well, when x is 2, 1 over x is 1 over 2, obviously. When x is -2, 1 over -2 is -1/2, and that should be pretty obvious. If you write it out, it looks pretty obvious. So the numbers I get over here are the same as the numbers I have here, but they're in different order. Okay, but they just happen to be the same. Now there's a 1 over x squared that you've seen if you've done the homework. Okay, where these numbers are like 1/4, and they're all positive because you're squaring. It's 1/4, 1, 4. Okay, and then down here it's 4, 1/4, 4, 1, 1/4. Okay, so that would be different. You'd have different numbers over here. At least some of them be different than the numbers you have over here. Here, the numbers are the same, just happen to be. Well, mainly, I want to get you used to the idea of domain and range. So now the domain of the extended function. Well, tell me. What's the domain of the curve? And what's the range of the curve? Give you just a couple of minutes to think about this. Okay, now, please be quiet. I know that the hilarity is too much to hold in. I've got to find a broken piece of white chalk. I've got them all over the place. Okay, now that my point was, we're trying to find a point in this domain, right? trying to find an X value that's in the domain. We've already identified 3/2 as one of the points that's not among the points on the basic function, the table function, okay? So what I did was I came out here, covered my eyes, turned around and flung a piece of chalk at the board. Now, my shoulder won't go any further than this. I really can't, kind of a dartboard motion, like overhand, but that's no fun. Okay, so I'm going to do it underhand. I'm going to close my eyes, I'm going to cover them, and I'm going to try to hit a point there. I'm not looking back. Okay, but I kind of know where it is. So we'll see if I luck out. Ready? Here we go. Ah, shoulder stuck. I was hit all the way over here. That was even worse than most of you did from where you were sitting. Of course, you were able to look. Okay. Okay. Now, my point is that finally, after many, many tries, we hit here, 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 here. Somebody got kind of close to a point right here. Finally, somebody hit the board up here, which gave us a vertical line that went through this graph. Okay. And then we estimated that this point here corresponded to about x equals negative 0.7. So finally, we've got a second point that's in the domain, okay? That isn't in the domain of the table, okay? Now, question is, what other points? Now, we can't have people responding on the video. So we'll pause the video a minute and see if we get some more points. Okay, somebody, I'd love to name you on the video here, but we can't do that. Somebody said, okay, it could be anywhere between 1/2 and 2, or between negative 1/2 and, or negative 2 and negative 1/2, right? Okay, so how are we going to write that? Well, to write that as negative 1/2. We want to do them in order from left to right. Okay, there's the interval from negative 2 to negative 1/2, right? Okay, so any number between here and here gives you a point on the graph with a y value. And then we use set notation. This is like a kind of a big U, stands for union, okay? It means we take the union of the interval from negative 2 to negative 1/2 with the interval from 1/2 to 2. Now you're going to see that in your homework. But that's your domain, okay? Now I'm not going to try to drag the range out of you, but you can see that the range consists of y values between 1/2 and 2, or between negative 2 and negative 1/2, right? So here's your domain. Got a question. Okay, so anyhow, in blue here is the domain. It's here and here. The range of the curve, well, it's all the y values that correspond to points on the curve. There's the range of your curve. Okay, and I can write that as okay, I didn't write it very well. It's kind of hard to read even up here. But it's exactly what we expect. -2, -1/2, union 1/2, 2. Okay. Now there's a question about absolute value. The absolute value is really probably the easiest of the toolkit functions as presented in the open math, okay? Now the absolute value, well, I'm going to assume people have seen absolute value, but if you haven't, I think you'll pick it up quickly. So let's do this. Let's do a table for X. And Y equals absolute value of X, okay? We have -2, -1, -1/2, 0, 1/2, 1, 2. Well, the table's really easy, okay? The absolute value of -2 is 2, okay? Now, let me give you a definition of absolute value. Intuitively, the absolute value of a negative number is just that number without the negative on it, okay? And the absolute value of 2 is 2, okay? And now you can probably tell me what the absolute values of -1 are. It's going to be 1. Absolute value of -1/2 is 1/2. Absolute value of 0 is 0. Absolute value of 1/2 is 1/2. Absolute value of 1 is 1. On the number line, now this is not a graph, this is just a single axis. I've got 0 here and 2 out here and -2 here. The absolute value of 2 is this distance. It's how far it is between 0 and 2. The absolute value of -2 the absolute value of X is how far it is from 0. We don't care if it's how far this direction or how far that direction, just how far it is from 0. Okay? There's a lot more I could say about absolute value. We've got like 2 minutes and I can't say it all. Okay? But that's a geometric interpretation of this thing. Okay? Now the graph is really easy. I'm just going to show you what the graph looks like, because if you graph the numbers in this table, you're going to get something that looks like this. Kind of like the x² function, except it's really pointy here. You don't want to get stabbed by this one. X² function is kind of blunt. It'll just bruise you. This one impale me. Okay? The other definition of the absolute value of X that you will probably see or have seen is that absolute value of X has a split definition. It equals -X if X is less than 0, and it equals X if X is greater than or equal to 0. Let's test this for X equals -2. Okay, so what's the absolute value of -2? Which branch does that belong on? Is -2 less than 0 or is it greater than or equal to 0? It's less than 0, right? Okay, so absolute value of -2 equals the negative of -2, which is 2, since -2 is less than 0. Okay? So if you got a negative number, it's the negative of that. Well, the negative of the number is the same distance from 0, okay, as the number, but on the other side of the axis. Okay, the negatives flip numbers across the 0, okay? Now that's, again, an important concept. It's a symmetry concept, and symmetry is really important in pre-calculus and understanding functions. Because, for example, the x squared, well, this is symmetric. If you have the value at x, all right, there's the value, right? Now, if you go to negative x, you go the same distance on the other side of the axis, you get the same value. So this point reflects over here, since its value at x is the same as its value at negative x. Now, that's something you probably aren't going to absorb instantly from me saying it. If you get a chance, you know, I've said several things in class that are worth pondering. So at some point, maybe even when you take pre-calculus, because this video will be there, okay? You might want to check it out, play it again, pick up on some of the insights that are kind of there with side comments that we didn't really emphasize, okay? Be to your profit to kind of review what we've done here at the beginning of the pre-calculus course and what we do for the next 3 weeks, because we're really now talking about topics in pre-calculus, preparing you for big topics, okay? So that's kind of where we are. Store that away, use it if you need it. And if you're doing fine, continue to do fine, okay? Oh man, hang on a minute. Don't walk in front of the camera. The camera just decided that it didn't want to be focused anymore. You probably pick it up with me. You know, I'm kind of focused. Let's see. Let's just get a good picture of that board. And maybe I'll do a little addendum with people around here. Just make sure we got most of it.